Welcome to Orbital Dynamics, Part 50. This part is based on excerpts from the book The Mechanical Universe. Here we'll talk about the Coriolis Force. It's a fictitious force similar to centrifugal motion. Let's say we apply a force, F equals ma0, on a reference frame. Think of this like a spaceship or train car. The force will cause the frame to accelerate. Here we apply a constant force so the frame continues to accelerate. We're observing this in an inertial frame that's not accelerating. Imagine an object moving in the frame that's not attached to anything. As the frame accelerates, the object in the inertial frame of reference stays fixed. If you're observing this from within the moving frame, it would appear that the object was accelerating to the left in the opposite direction of the force applied to the moving frame. The force F would equal minus m times the acceleration a0. In Part 43, we talked about how a point located at a distance r from the axis of a rotating frame with uniform angular speed omega is accelerated at a rate omega squared r away from the axis in that frame. We call this a centrifugal force. When an object moves with respect to a rotating frame, the centrifugal force is supplemented by another inertial force called the Coriolis Force. Consider a puck crossing the axis of a rotating disk. If there's no friction, the puck moves in a straight line. Let's say it moves with a constant velocity v in the frame we're in, an inertial, non-accelerating, non-rotating frame. The rotating disk turns clockwise with an angular speed of omega. If you're on the disk, the rest of the world would be rotating in the opposite direction, clockwise. In the rotating frame, the puck appears to turn clockwise following a curved path. This is the Coriolis force, an inertial force in the rotating frame that accounts for the curvature that's not present in the inertial frame. Here's what that Coriolis motion looks like from both an inertial frame of reference and a rotating frame of reference. On the left, the object moves at a constant velocity while the disk rotates. We're observing this from our frame of reference, which is an inertial frame of reference. The object moves at a constant velocity in a straight line. That's inertial motion. No forces are acting upon the moving object. Now let's look at this in the rotating frame of reference, as if you're sitting on the disk. The object now travels along a curved line. This is how Coriolis motion occurs. Next, we'll show the two side by side. The left is viewed from an inertial frame of reference. The right is from the rotating frame of reference. From the rotating frame of reference, since the object does not follow a straight line, there must be a force acting upon it. We know from the inertial frame that the object has no forces acting upon it. In the rotating frame, we see a fictitious Coriolis force that explains the object's motion. Let's look at the path the object travels in a small time interval, delta t. The disk spins in this same time period. Here the object starts at the center of the disk and travels to the right to point P. The displacement is velocity times time, v times delta t. The puck is deflected at an angle delta theta. Delta theta is the angular speed, omega times delta t. The distance delta s the puck is displaced is r times delta theta, where delta theta is expressed as radians. Remember that if the angle is expressed in radians, the arc length is the radius of the arc times the angle in radians. We can substitute omega delta t for delta omega. The displacement, delta s, thus equals r omega delta t. We can substitute v delta t for r. There are two delta t's here. That simplifies to v omega delta t squared. The formula for change in displacement is r equals v delta t. We can express that in terms of acceleration. 1/2 a delta t squared. Delta theta is also a displacement. V omega delta t squared equals 1/2 a delta t squared. Note that the acceleration in this equation is different from the acceleration that causes the displacement r. Here we're considering the displacement delta s. There's a delta t squared on both sides of this equation. Those cancel out. We can then multiply both sides of the equation by 2. The acceleration that created the displacement, delta s, is 2 times v times omega. That's 2 times the linear velocity of the puck times the rotational velocity of the disk. The Coriolis force is mass times acceleration, which equals 2m v omega. Notice that in the diagram we've depicted the angular velocity omega as a vector that is normal to both the rotation and the linear velocity of the object. The deflection is perpendicular to both the axis of rotation and the velocity vector. It is perpendicular to vectors omega and v. The Coriolis force can be expressed as a vector, minus 2 m omega cross v. This formula only works if the object is very near the axis of rotation. There, the velocity of the object in the inertial frame is nearly equal to the velocity in the rotating frame. As the object moves farther away from the center, the velocities differ. The proper equation uses the velocity in the rotating frame. This is the general equation for Coriolis force. The fictitious Coriolis force changes both the direction and the speed along the path. I'm not going to derive v prime. For orbital dynamics, it's important to understand the Coriolis force. We don't, however, need to be able to compute the force. The direction of the Coriolis force follows the law of conservation of angular momentum. When the object passes through the center of the rotating disk, it has no angular momentum. In the inertial frame, it moves through the center in a straight line, conserving angular momentum. It has zero angular speed. This requires, however, that it move to the right, which implies an angular speed in the rotating frame. One can deduce either from the Coriolis force in the rotating frame or from the lack of angular momentum in the inertial frame that the trajectory curves to the right in a frame rotating counterclockwise. If the frame were moving clockwise, the motion would be to the left. In this animation, the motion in the inertial frame is elliptical. The motion in the rotating frame is circular. The magnitude of the Coriolis force is appreciable on a turntable or merry-go-round. Here's the force equation we derived. Here's the acceleration. If the angular velocity omega is 1 radian per second and v prime is 5 meters per second, the Coriolis acceleration is 2 omega v primed, or 10 meters per second squared, about equal to gravitational acceleration. Away from the center of the rotating disk, Coriolis and centrifugal forces are both present in the rotating frame. Imagine an object tethered by a string of length r. From the inertial frame of reference, it circles with the disk at its angular speed, omega, under the centripetal force, m omega squared r. That force is supplied by the string. In the rotating frame, the object is in equilibrium under opposing pull of the centrifugal force and the string tension. Now let's cut the string at some point. That releases the object. In the inertial frame, the object now moves in a straight line. It's not acted upon by any forces. It travels at a constant velocity. In the rotating frame, it's at rest until the string is cut, and then it accelerates radially outward under the action of the centrifugal force. As it gains velocity, it also feels the Coriolis force, which deflects it to the right. The Coriolis force associated with the Earth's rotation is much weaker than the effects I described on the previous slides. The Earth rotates only once per day. That's an angular speed of 7.272 times 10 to the minus fifth radians per second. Even at slow speeds of, say, 50 meters per second, the Coriolis acceleration, 2 omega v primed, is 7.272 times 10 to the minus 3 meters per second squared, far less than g at 9.81 meters per second squared. The Coriolis effect over a sufficient period of time does have striking effects. Trajectories curve slowly to the right in the northern hemisphere. The Earth rotates counterclockwise as seen from above the North Pole. In the southern hemisphere, trajectories curve slowly to the left. High above the Earth, air in high-pressure zones tend to flow outward in all directions. In the northern hemisphere, the Coriolis force deflects air currents to the right. The result is northwest winds.